Hi and welcome everyone. My name is Niklas Funk and I'm from TU Darmstadt and very happy to present you our work on graph-based reinforcement learning meets mixed integer programs, an application to 3D robot assembly discovery. 3D robot assembly discovery is the task of having to build arbitrary 3D structures given a set of building blocks while considering the robot in the loop. Additionally, we have to ensure structural stability throughout the whole construction process. Robot assembly discovery thus exhibits a twofold combinatorial complexity of on the one hand having to decide which parts have to be placed where, and on the other hand we also have to come up with a feasible sequence of execution. One potential approach to robot assembly discovery could be task and motion planning methods that run a full model-based optimization. Yet, contrary to robot assembly discovery, they typically require an explicitly pre-specified goal state. Despite the limited complexity, they are still computationally very expensive. On the other end of the spectrum are end-to-end learning approaches that directly map from problem description to low-level actions. They benefit from flexible graph-based representations, however exhibit limited interpretability. Indeed, in our previous work, we found limits in generalization. Thus, in this work, we propose a novel hybrid method based on the combination of graph-based reinforcement learning and mixed integer programs. Our novel proposed hierarchical approach consists of 3 levels. On the highest level, we run a mixed integer linear program to handle resource assignment, which is followed by an intermediate level graph-based reinforcement learning agents for task sequencing. On the lowest level, we run a classical grasp and motion planning to put the desired actions into practice on the robot's joint level. In the following, I want to explain you the interplay between the two highest levels in the simplified 2D robot assembly discovery environment that is shown in the top left-hand corner, which consists of 2 blocks that are still to be placed in white, as well as the grid in which the pink voxels signal desired cells that should be filled upon the assembly process, while the green voxels should remain unoccupied. On the highest level, to formulate everything as a mixed integer linear program, we do not consider structural stability, robotic feasibility, as well as task sequencing. At the core of this MILP formulation is the so-called grid occupancy vector X, whose entries signal whether a specific cell of the grid is filled or not. Next, we make use of so-called vectors G that describe how the grid occupancy changes on adding the blocks in all potential locations. We can combine all of those vectors together into a matrix M, and we can also include decision variables for every vector G. Thus, those decision variables effectively control whether a block is placed in a certain pose or not. Therefore, we can also express the grid occupancy X as matrix vector product between M and D. This already concludes the high-level MILP formulation in which the final objective is given by C transpose times M times D, in which C is a weighting vector that incentivizes filling the pink desired voxels while the green ones should remain unoccupied. Therefore, the MILP resolves the combinatorial complexity of which part type has to be placed where. However, as previously mentioned, the high-level MILP does not consider structural stability, robotic feasibility, as well as task sequencing. Those challenging, nonlinear, and combinatorial constraints thus have to be captured by this intermediate level, for which we propose to employ a graph-based reinforcement learning framework making use of model-free Q-learning. This intermediate level works as follows. Starting from the input scene, we transform it into a graph-based representation, in which the white nodes correspond to the building blocks, whereas the pink and green ones represent the voxels of the grid. Next, follow 3 rounds of message passing using a multi-head attention approach. This results in an encoded version of the graph, in which we can estimate the Q values for all of the available actions. However, now we make use of the prior knowledge from the MILP in that we only consider the actions that have previously been proposed by it. The MILP therefore efficiently shrinks the exploration space that we have to consider on this level. On the contrary, this level benefits the MILP as it is capable of capturing many nonlinear and combinatorial constraints that have not been modeled previously. Now we turn into the experimental section. Our first experiment was targeted at the question, is this high-level MILP really needed, or can we just achieve the same or even better performance if we apply an end-to-end graph-based reinforcement learning approach? As you can see here in this table, our proposed approach is indeed effective as it doubles the reward in both training and testing environments. In the second line of experiments, we tried to answer the question on how effective is the intermediate level GNN by comparing our proposed approach against the heuristic. This heuristic also gets as input the solution of the MILP, but then performs action selection by selecting randomly from all the actions that result in a stable block placement. As we can see in the table, already in the training environment, our proposed approach doubles the accumulated reward, whereas in the more complicated testing environments, we even achieve performance increases by factors of 4. The findings are also underlined in these videos, in which you can see that task sequencing using the heuristic is not sufficient, because it results in many collisions due to the tight blazing space. In contrast, our proposed method performs way better. Finally, we were also able to show real-world transfer of our complicated method. We thus conclude that it can indeed resolve the inherent difficulties of robot assembly discovery. It is invariant to problem size and shows improved generalization compared to end-to-end approaches. Thanks a lot for your attention.